The broadcast is now starting. All attendees are in listen-only mode.
Hey everybody, welcome back to Young Engineers of Today. I hope you've had a good weekend. I hope you had a good week so far. And I hope you're ready to continue with Fly to Learn because like I said, we got a few more lessons left with this. We're going to try and finish this out and we'll probably end the semester with this. So we will do a little bit more flying and experimenting and plane building today, and then we'll break. So let's see here. I think, yeah, we're in airplane design, putting it all together. So the idea here was that um, we've learned a whole bunch of different concepts that are used in building an airplane, aerodynamics and power to weight ratio, and wing loading, and just a whole bunch of different things. And what we're interested in doing is taking all of these concepts that we have and putting them all together to make a functioning airplane design. So we've learned about science, engineering, and aviation. We've flown a twin-engine airplane, haven't landed on a carrier deck. Lengthen the wings of an airplane, shorten the tail of the airplane, just to see how it messes with everything. Played with different engine powers and weights, and all sorts of different things. So let's put it all together and design your own airplane. So a lot of this is, hey Calder, a lot of this is also going to involve calculations and stuff like that too, just so we can get more comfortable with the math side of things. So let me bring up my calculator as well, just so you can watch along as I'm calculating things. But the other really sort of important thing about all of this is learning about the different engineering, math, and science principles that go into designing an airplane. So we've been doing research with every Fly to Learn lesson, which is sort of learning the different frameworks and the concepts that are fundamental to designing an airplane. Research has also included looking at what other people in businesses are designing and building so that you can understand how things might be affected. Research might also study what the public wants in an airplane. So you might discover that people want an airplane that's faster and more fuel efficient than is for sale, or that you might discover a new way to build airplanes that is cheaper than conventional methods. So these are all things that you want to take into account as an engineer. They're actually, it's being an engineer is not just about being able to build the thing that you want. It's also being able to build it with a low amount of money and time required, because as we covered in the very beginning of the semester, or at least the beginning of the fall semester, part of the engineering design process is making sure that your design is repeatable on a large scale. So if a project takes more time, usually costs increase, and also the engineer may not be able to wait. But here's the planning stage in the engineering process. We've got identify opportunities, brainstorm ideas, select an idea that seems the most promising, model that idea, at least mathematically, and then test the idea. So as the explanation says down here, you may begin the planning process by identifying an opportunity. In engineering, a need or a problem should always be considered an opportunity. We don't have personal planes. Everybody's driving cars instead of flying around in the sky. There's an opportunity right there. It's not a bad philosophy for life in general. You then brainstorm to generate several possible solutions. You select your favorite solution, and then you mathematically model your idea. So you find, okay, so what if we put turbines instead of wheels on every single car out there so that we could have flying cars? Well, then you might model mathematically that possibility. Okay, so how much lift could a turbine create How much lift would 4 turbines create? Would it be enough to lift up a car? How much gas would it consume? Could we have like a hybrid system so that the car could, be using a battery and gas? And how far would it be able to fly given that? How controllable would it be? Yeah, sure. That should be fine. At the very least, just to, just to sit in. Um, yeah, no worries. He's in ninth grade. Yeah, you could have him come by and check it out and just see. I'm sure that would be okay with Mr. Dubik, more than likely. Yeah, definitely. Um, but yeah, it's better to do some calculations before you start building things, because you work smarter and faster with your brain than with your hands. That's just an unfortunate fact of life. We build tools to make things easier for us, but tools, some of the more moving parts you have in a process, the more efficiency is lost. And our hands are tools like anything else. So we're not going to be able to directly translate stuff we want to do in our brain to stuff that we end up doing with our hands. I mean, seeing people miss a baseball when they're trying to catch it, um, that's evidence of that. But anyway, being able to model things mathematically, we'd be able to more quickly prototype things. So maybe we could find in our math, hey, 4 turbines would not be strong enough to lift up a car, or it would, but then the car would run out of gas 15 minutes later. So it also involves kind of finding out what's a feasible solution. If it survives the mathematical modeling, then you can build a proof of concept. Proof of concept demonstrates whether an idea is feasible or possible. So yeah, proof of concept is usually narrow in focus. For example, if you're designing a better airfoil, you would build a small section of the wing, not the entire wing, and certainly not the airplane. So maybe you focus on turbines that are more efficient so that you can lift up a car. So you might build one of these more efficient turbines just as a proof of concept and see if it generates as much lift as you anticipate. Then if it does work and you test the idea and it works out, then you can expand that proof of concept to be on a car, that sort of a thing. So the prototype phase has a few steps that may be repeated many. Oh, okay. Yep. That may be repeated many times. It comes across to the other side. So your goal should be for the prototype to get better with each repetition or iteration. Iteration is an important part of the engineering process because nobody is going to be able to make a working design on the first try. It's just not possible. Um, you always want to make sure that at the very least, if you don't get it wrong, or if you don't get it right on the first try, that at least you're learning something from it, so that the next time you try, it's a little bit better. Because engineering is all about trying and failing over and over again, and just learning a little bit more each time. Um, so in this case, you would put the engineering design process to work by designing your own airplane, building your design in PlaneMaker, and then flying your design in X-Plane. Um, Let's assume that during the research and planning phases, you developed the following design specifications. You wanted a 4-passenger airplane, including the pilot. You want it so that each passenger can bring 20 pounds of luggage. You want it so that the plane has a 150 knot cruise speed, so 150 miles an hour, but as the crow flies, and an 800 nautical mile range. So now let's mathematically model your plane design. Since this is your first airplane, we will focus on the weight, wings, power, and range. Once we complete these calculations, you can build a prototype airplane in PlaneMaker. So we'll need to calculate the weight of your airplane because all of the other design calculations are based on the weight of your airplane without the weight of the fuel. So the average passenger weight is 170 pounds. Okay, so how much luggage will each passenger carry? We already know that each passenger is going to bring 20 pounds. Look at that 2 and that 0. So the average weight per passenger plus luggage, I mean, that's pretty simple. We're just going to add these two together. So it's going to be 190 pounds. Because if each person weighs on average 170 and each person is bringing 20 pounds, how much do they weigh plus luggage? 170 plus 20, 190. How many passengers will the plane be carrying, including the pilot? Well, we got a 4-passenger airplane, including the pilot, so 4 total. And the total payload weight is the number of passengers times the average weight. So this is one of those things where engineers could totally split hairs. Are we assuming that the pilot is going to be bringing along 20 pounds of luggage, or is he just ferrying them so he's not going to be carrying 20 pounds of luggage? Um, because that could affect the final weight necessary. But let's assume, for the sake of argument, that the pilot is bringing along luggage, so we can just do some nice, easy mathematics. Let's pull up our calculator. If we've got 4 people and each one is carrying 100, or each one is adding 190 pounds to the plane, 4 times 190, 760. So total payload weight is the number of passengers times the average weight. It's going to be 760 pounds. So the total payload weight on the plane is going to be 760 pounds. Most modern airplane designers have learned through past experience that the airplane weight can be determined by dividing the total payload weight by 30%, or 0.3. This is an example of a rule of thumb. A rule of thumb is a rough estimation. Engineers often use rough estimations at the start of the design process. So, all right, well, this is interesting. I guess they're trying to say that the payload weight, because when you divide by a number less than 1, you're making the number larger. So that's why this is kind of a strange way to put this. So if we divide 760 divided by, or if we divide 760 by 0.3, you get 2,533.3 repeating. So $2,533. That would make sense, I suppose, considering this is going to be the weight of the airplane overall. I guess it's just an interesting way of saying that the total payload weight is a third of the gross airplane weight. Anyway, gross airplane weight is 2,533 pounds, so roughly 2,500. Yeah, all right. There we go. Let's get rid of our writing down here. So please note that the gross airplane weight or takeoff weight is the empty airplane weight plus the payload weight plus the fuel weight. Alrighty. So we know so far in our collection of information that the gross airplane weight is going to be 2,533 pounds. So for the wings, now we need to calculate the size of the wings in our airplane. First, we're going to calculate the wing loading and then determine the wing area, aspect ratio, and finally wingspan. So we already know that the gross airplane weight is 2,533 pounds. Now the standard wing loading, this is going to be interesting. The standard wing loading is W divided by S, which is equal to 2.24 times, I think that's a 2. That might be a 3. Let me see if I can't zoom in and make it easier to read. No, that just blows it up more. Okie dokie. The world may never know if that's a 2 or a 3. Oh, good Lord. Hold on. All right, we're back to where we were. I think that's a 3 because they wouldn't be putting the digit there otherwise. So 2.24 times the cube root of the gross airplane weight minus 6. So if we take the gross airplane weight and we take the cube root of it, we get 13.63, 214,253, blah, blah, blah. Subtract 6 from it, and we get 7.63, 214, blah, blah, blah. Then we multiply it by 2.24, and we get 17.1. Let's say 17.1. 17.1. So our standard wing loading is 17.1 pounds per square foot of wing surface. Unfortunately, we don't really have an explanation as to why this is sort of a standardized um, calculation for it. Why? How can we get standard wing loading by taking the cube root of the gross airplane weight minus 6 and then multiplying it by 2.24? That's not explained here. So for now, it's just got to be memorized, which is annoying. I really don't like it when it's just something that's memorized as opposed to actually knowing why uh, something like that exists. But hey, we've got a standard wing loading. So the high wing loading range is going to be standard wing loading times 1.3. Now, this is going to give us basically sort of the maximum that we can stress the wings. Um, this is going to be the sort of the highest safe wing loading. So this could either mean this is the most that we could weigh down the plane, which I don't recommend, or this could mean this is the smallest that we can make the wings. The smallest that we can make the wings might make sense because if we make the wings smaller, we make the plane more maneuverable, and maybe it'll use more fuel, but well, whatever. So if we multiply this by 1.3, we get 22.24. And so let's actually note this. So standard wing loading is 17.1 pounds per square foot. High, let's say this is stand wing loading so that we keep it all in the same line. High wing loading is 22.2 pounds per square foot. And low wing loading, so let's divide it by 1.3 again to bring it back to the original value and multiply it by 0.7, which should give us a lower value. And this gives us 11.9, let's say 12.0. Do a little bit of rounding because 11.96 rounds up to 12. So 12 pounds per square foot. And again, this relates back to we could either lower the weight of the plane or we can make the wings larger. Making the wings larger means that the plane is less maneuverable, however, it requires less speed to take off and less fuel to fly in general. So higher wing loading means higher stall speeds and longer takeoffs and landings, and modern light planes exhibit wing loading less than 20 pounds per square foot. So high wing loading is a little bit high for a light plane. The wing area, which is the gross airplane weight, which we already have is 2,533 pounds, and the wing load range, so that's going to be the standard wing loading. Yeah, it's going to be the standard wing loading. And the wing area, which is going to be the gross airplane weight divided by the wing loading. So if we take our calculator and our notes, and we say 2,533 divided by 17.1. That gives us wing area 148.1 feet squared. And that's exciting, right? But yeah, so what this is doing right now is this is giving us a total square footage of the wings. So how big we want the wings to be for standard wing loading. So now we have an airplane weight, which was given to us with the average passenger weight and all of the passengers and everything like that. And then we sort of roughly estimated the gross airplane weight from there. Then we got the wing area, which we took the standard wing loading, which is a reasonable sort of guideline for how much stress the wing should be under at any given point, and calculated the wing area from that. So we have a rough idea of two of our plane's characteristics in our head already. And all we've done is started with how many passengers this plane is going to have. So it's kind of neat. Anyway, wingspan. So we need to decide on the aspect ratio first. The aspect ratio of modern light planes is 6 to 8. So we're going to split the difference and use 7 as the aspect ratio. Remember, the aspect ratio is the ratio of the width of the wing to the length of the wing. So the aspect ratio is 7. The wing area is going to be 148.1. The wingspan, in this case, is going to be the wing area times the aspect ratio, and then take the square root of it. So let's go ahead and calculate that. I know, it's tons of math, but it's not hard math either. It's just tons of math. So anyway, wingspan is going to be 148.1 because that is our wing area. Then it's going to be times the aspect ratio, so times 7, which gives us 1036.7. So we've got that whole area right there. So we've got the square root of 1036.7. Let's take the square root of that. So our wingspan is going to be 32 feet. So again, all we were given was how much this plane has to carry, and we've got a wingspan. Now the chord, which is the width of the wing, is going to be the wing area divided by the wingspan. So let's go ahead and calculate that. 148.1 divided by 32. Our chord, if I spell it correctly, is going to be 4 feet. So not only do we have the wing area, we have the wing dimensions now too. Cool. So the power required equals drag times velocity. So now that we've done the wings, let's worry about the engine power. The calculations to determine power are beyond the scope of this lesson. All right, fair enough. Let's assume you need 150 horsepower. This kind of horsepower is called brake horsepower. Remember that whole explanation with brake horsepower versus cruise horsepower versus thrust horsepower, where brake horsepower is the rough, sort of the raw power that the engine can create. Thrust horsepower is how much forward power the plane has after the engine translates its explosions and everything to the propeller spinning and the plane moving forward as a result of that. And then the cruise horsepower is basically how safe you can, or how much you can push the engine consistently, safely. So that is to say, you don't want to be running the engine at 100% all the time forever because you're going to burn out the engine pretty bad that way. So you run it at about 70% in order to keep it, or 75%, I suppose, in order to keep it sort of safely running consistently. So that's like your cruise horsepower or rated horsepower. So a modern propeller is 80% efficient in converting the brake horsepower into actual thrust. This kind of horsepower is called thrust horsepower. So, okay, the thing that we just talked about. So if we assume that we have 150 brake horsepower necessary in order to make the plane fly, if we multiply that, times 0.8, that gives us 80% of 150, which is our our thrust horsepower. So we have 120 thrust horsepower. So let's break these up. Brake horsepower, 150 HP. Oh, nice, yeah. Thrust horsepower, 120 HP. So then we actually want more horsepower than that because we do not want to operate engines at full horsepower. Oh, awesome. Well, enjoy it. Oh, that came out all distorted, Cademan. Oh, wait, I see it now. 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 All right, so yeah, we don't want to operate the engines at yeah, no, I hear you. The engines at full power because engines running at full power run out sooner and they're less fuel efficient. Instead, we want the engines to operate at 75% of thrust horsepower. This horsepower is called rated horsepower. All right, so take 120, we multiply it times 0.75, and we get 90. So our rated HP is 90 horsepower. Wicked. That's fun. So now that we've calculated our horsepower, let's see how far we can fly our airplane on a tank of fuel. We begin by calculating how much fuel the plane will carry. We then calculate the total fuel available by multiplying gross airplane weight times 15%. 15% is another rule of thumb used by engineers to design airplanes. So, in yet another onslaught of math, we take everything we know in order to figure out exactly how far our airplane can go in nautical miles. So we've got our gross airplane weight, which we know is 2,533 pounds. We take the total fuel available, which is going to be the gross airplane weight times 15%. So fuel available is going to be 2,533 times 0.15. 379.95 pounds of fuel. So let's say that's 380 pounds of fuel. 380 BS. Then the payload weight. The payload weight I did not write down. The payload weight is, hold on, divided by 0.3. Nope, wait, wrong direction. 760. That's right. So we've got 380 pounds of fuel available. Payload weight is 760 pounds. The empty weight of the plane is going to be the gross weight minus the fuel weight plus the payload weight. Hey, Cohen. Yeah, I was wondering what you were. I was surprised to see you in this one instead of the high school one. All right, so empty weight. What we're going to do is we're going to add our. This is. We're going to add our fuel weight plus our payload weight, which gives us 1,140. Oh, really? Interesting. Yeah, I don't know then. Well, at any rate, here you are. You can always join the next one if you'd like. I think I'm not entirely sure 100% how that works on the other end, but if not, at least you got this. And then I'll put up the videos for the high school one as well if you're curious about it later on and you can't join. Yeah, okay, that's fair. Well, dang it. We'll get it figured out. So 2,533 minus 1,140 gives us an empty weight of 1,393 pounds. That is interesting. I don't know why I did that. I shouldn't have done that. Well. All right, so our cruise speed is going to be 150 knots. Our specific fuel consumption is 0.5 pounds per horsepower. So the range is equal to total fuel available times the cruise speed divided by the specific fuel consumption times the thrust horsepower. Alrighty, so total fuel available is going to be 380 pounds. So 380. And then we're going to multiply that by cruise speed, which is 150 knots. That gives us 57,000. Then we've got our specific fuel consumption, which is 0.5, times the thrust horsepower, which is, thrust horsepower is 120 horsepower, which is 60. And then we do 57,000 divided by 60. And this gives us a range of 950 nautical miles. Or NM. Or N miles, whatever. It depends upon whatever your context, because NM can also be nanometers. And I'm pretty sure our plane goes further than 950 nanometers. All right, so that was 950 nautical miles, and we wanted our plane to have an 800 nautical mile range. So excellent. We've met our design specifications. We have a plane that goes 150 knots, can carry 4 passengers, including the pilot, along with 20 pounds of luggage, and can fly as far as 950 nautical miles, which is like a third of the way across the U.S.-ish. That's not bad. For like a little tiny plane, that's not bad at all. It'll take forever. I mean, 150 knots and 950 nautical miles, you can be flying for a while. But regardless, you could do it. What computer do I recommend? Well, that largely depends upon what you're looking to do. There are a lot of different things as far as that's concerned, which I know is not exactly a satisfying question or answer to hear to that question, but it really is that there's a lot to unpack in that question. That's all. Oh, personally, I prefer. I mean, they all have their pros and cons, you know. Macs are good if you don't really want to get your hands dirty, or if you're very comfortable with the command line and you don't want a Linux system for whatever reason. PCs are good for the wide variety of software that they have and the size of the market. Although, you know, Macs are definitely, you know, pretty close there. And yeah, I used to be very much on the Mac side of things, but I've evened out a lot in the last few years. I wouldn't necessarily say I'm a Windows person. If anything, I tend to lean towards Linux systems, but I also just use a lot of the software that I like is on Windows, so I use it. Screen recorder. I just use the screen recording software that comes with GoToWebinar for these. Although if you get like a nice NVIDIA or AM or ATI card, you can probably get you can probably use the screen recording software that comes with that by default, and that usually does pretty well. Although sometimes it only triggers whenever the card is engaged. So if it's got some kind of 3D rendering or something like that on it, then the card will say, hey, okay, you know, my time to shine and record things. Otherwise, you know, it might have a hard time. Anyway, so now that we've done the calculations on that, nice. Yeah, I've got an NVIDIA card in mine. We're ready to build a prototype in PlaneMaker. So since you're using PlaneMaker, you can quickly build your prototype, which is a virtual airplane, by modifying the RV10. This will allow you to quickly try out your design safely and, you know, cheaply. Complete the table below. I'm just going to say that out loud because I'm reading things without really paying attention to what I'm reading. Oh, good job, me. So we're going to begin by entering your values in the second column, and then you'll need to calculate half the wingspan value by dividing the wingspan value by 2. And then we're going to open the PlaneMaker for the RV10 airplane and enter in the appropriate values. So gross weights, we know what that's going to be. That's going to be 2,533 pounds. So we can just go whoop, 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 and write it right in here. Yay. Fuel weight. Fuel weight is going to be 380 pounds. I cannot tell you how much of a challenge it is to try and write numbers into something this small using a mouse. Um, empty weights is going to be 1,393 pounds. Whoop, put that, close that 9 off. Wingspan, where we got it? Wingspan is going to be 32 feet. I know this is totally thrilling to watch me do this. Half of wingspan, oh, that's going to be 16 because I'm super good at math and I know how to divide a 32 by 2. Chord is going to be 4 feet. Rated horsepower is going to be 90 horsepower. And so really all you're going to do is you're going to go into the plane maker for X-Plane and set up everything as it is here. So let me go ahead and get to the plane maker, get that opened. So I'm going to try and, there we go. I'm trying not overwrite this area. So let's see here. So if we're going to set up the weight, we need to go into, as the table says here, the weight and balance menu and modify the fields that they provide here. So, okie dokie. Already off to a, there we go, weight and balance. I'm blind. All right. So empty weight is going to be 1,393. So 1393. And then fuel load is going to be our fuel weight. So 380, that's already in there. Fantastic. Our gross weight is going to be the maximum weights. So we're going to change that to 2,533. Perfect. So we filled out our fuel load, our empty weight, and our gross weight, maximum weight. So we were done with the weight area. We can go ahead and close that out. And just so you guys can see the whole thing, I'm going to bring the menu back over here. Sure, I was just going to run through it again. I wasn't going to. I mean, this stuff's all stuff that you've written down too. So you just want to match the fields up to the values that you put in there. But yeah, I can go over that again if you'd like. Also, just so we got everybody on the same page, once you've got these fields, once you've got the values into these fields, go ahead and raise your hand. Alrighty, got a couple of hands. Well, one hand, actually, one hand so far. Two hands. Three hands. Alrighty. Yeah, once we've got a couple more hands up, we'll go ahead and move forward with this. Alrighty, let's get the rest of these values entered in so you guys can spend the last of the time doing some test flying. So I'm going to close out the weight and balance menu. As we can see, the next values are going to go into the wings menu. So let's go ahead and open up that menu. So if we go to wings, so we've got semi-length and root and tip chords, which should be pretty easy. As you can see, semi-length is here and root and tip chords, perfect. They're right next to one another. So half the wingspan is 16. That's going to go into semi-length, 1600. Then the root and tip chords are each going to be 4 feet even. And then we'll be done with wings there. So I'll go ahead and keep this up for another minute and go ahead and raise your hands once you've entered in the appropriate values there. As if to prove my point, that's the driver I'm using. Thank you, GeForce. Alrighty. I know we ain't got no hands up, but let's get this squared away so that you guys can fly with it. So close that out. Oh my. All right, so we've got an issue here. Let's set the semi-length to 16 on both wings and 4. Nope. That does not fix the issue. That, in fact, makes it worse. All right, so if we change the vert arm to 2, no, we'll keep it at 0. All right, so our plane design is a little bit more complicated by the fact that we cannot, so if we re-enter 16 in here, does it recalculate that one? No, it does not. Yours is perfect. Oh, something happened with mine then. Don't save. Well, I'll go ahead and pretend that I've already done the weight on mine, and I'll just do the wings one more time. So wing 1600, 400, 400. All right, I just had to change a couple of things about it. Most of you guys shouldn't have to worry about that. It should be fine. I don't think anybody should really have to worry about that. I don't know why mine was freaking out so bad. Anyway, last thing we're going to do is engine specs. So go to standard and then engine specs. And this is going to be under max allowable power. So let's find max allowable power. Max allowable. Well, we've got maximum power, but not max allowable power. Well, let's put our brake horsepower in the maximum power because that is going to be the maximum power. Actually, our thrust horsepower, excuse me, 120. So we put our thrust horsepower inside maximum power. We should know that if you run the plane at 75%, you'll be able to hit 90 horsepower. Yep, you can go ahead and fly the plane. Okay, Caveman, you don't have to keep doing that. You can go ahead and fly the plane. Do that for a couple of minutes, and then we'll do actually let's do the poll questions now so that you can spend the closeout time flying the plane or asking questions, and then we can break for the weekend as well. So first poll question incoming. %. So 5, 4, 3, 2, 1. Close. Glad you guys enjoyed it for the most part. Again, we should be. Well, much appreciated, Cohen. All right, we're at 56%, so let's get a couple more people to vote in on it, and then we can close out this question. 67, so 5, 4, 3, 2, 1. Close. Glad to hear it, and thank you, Cohen. But yeah, so that's going to do it for today. You guys can do some test flying with your newly designed plane if you'd like. If you have any questions, I'm here. It doesn't even have to be about the lesson. It could just be about, whatever. Otherwise, you're more than welcome to head out. Have a wonderful weekend. There are labs on Thursday and Saturday. Yeah, you guys have a great weekend otherwise. All right, you too, Cohen. Have a great weekend. No problem. Thank you. You too, Liam. Have a good weekend. See you later, Calder. See you later, Ethan. Take it easy.